So using the Bohr model of the hydrogen atom, which is the incorrect model, but it's an easy approximation, the electron orbits the proton, right? So since there's a hydrogen atom, it's a hydrogen atom, there's only one proton and one electron, and that has a radius of 0.53 times 10 to the minus 10 meters. The charge here that we're going to use is the charge Q of equal to 1.6 times 10 to the minus 19 coulomb. That's the charge of a proton, and minus that would be the charge of an electron here. Okay, so for part A, okay, we're asked to calculate the electric potential at the electron's orbit due to the proton. So the potential V is going to be equal to the constant K, which is 1 over 4 pi epsilon naught. It's equal to 8.99 times 10 to the 9 Newton times meter squared per coulomb squared. It's a common constant you can look up, times the charge Q divided by the distance R. Plugging those values into this expression, we find that the potential is 27 volts. And we can box that in as our solution for part A. Okay. For part B, the kinetic energy here can be found from the fact that the magnitude of the net force on the electron, which is an attraction by the proton, is causing the circular motion. So therefore, the kinetic energy, K, E, is equal to 1/2 mv squared, right? Which is going to be equal to 1/2 K times the charge Q times the magnitude of the charge of the electron, which is minus Q, divided by the distance between squared. And where did we get that from? Well, we got that from the fact that the mass times the speed squared divided by R is the force. Okay, which the force here, of course, using Coulomb's law is K Q times minus Q, the magnitude of minus Q, divided by R squared. So, and I actually had a typo. This would be over R, right? So then just plugging in mv squared for our KE value, we find that mv squared is equal to KQ times minus the magnitude of minus Q over R. So that's where we got that. Now plugging those values that we have into this expression, we find that this is equal to 2.2 times 10 to the minus 18. And the units there would be joules. You can then convert from joules to electron volts, and this is equal to 14 electron volts. You can box this in as your solution for part B. Let's not cross out that 18 there. Okay. Now moving on to part C. So the total energy then here for part C of the electron is going to be the sum of the kinetic energy and the potential energy. You can use equation 17-2a to find the potential energy, and it's negative since the electron here has negative charge. So the total energy is going to be equal to the potential energy plus the kinetic energy. Okay. Well, we just found the kinetic energy in the previous question, and the potential energy is going to be minus the charge Q times the potential V, okay, then plus the kinetic energy. We found the potential V in part A, so plugging all those values into this expression, we find this is equal to negative 2.2 times 10 to the minus 18 joules. Okay, well, this is just negative the answer that we got in part B, right? So this is just negative 14 electron volts. We can box that in as our solution to part C. Okay. Now for part D, So if the electron is taken to infinity at rest, then both its potential energy and its kinetic energy would be zero, right? At infinity, there's no potential energy, and if its kinetic energy is zero, right? The amount of energy needed by the electron to have a total energy of zero is just the opposite to answer of part C. So it would be minus E. You can box that in as a solution for D.